Okay, so this problem says a rigid body with a cylindrical cross-section is released from the top of a 30-degree incline. It rolls 10 meters to the bottom in 2.6 seconds. Find the moment of inertia of the body in terms of its mass and radius. Okay. So the angle of the incline is 30 degrees. So this is a cylinder and it's rolling without slipping. And the center of mass acceleration is given by g sine theta 1 plus I center of mass, meaning you're calculating the moment of inertia but the center of mass, divided by m r squared. M is the mass of the object and r is its radius. Okay. And what they want to find, what they're asking you is, okay, so it's some constant times mr squared. They're asking you what is this constant. So for instance, if this were a sphere, that would be 2/5. If it was a uniform disk, that would be 1/2. If it were a ring, that would be 1, and so on. Okay? So depending on how the mass is distributed. Yeah. All right. Well, see, we can calculate this. It rolls down 10 meters. 10 meters is roughly half the width of this room. So from the ceiling to the bottom here, it's rolling down in 2.6 seconds. Okay? So we'll say this is the x-axis, and x minus x naught equal to v naught t plus 1/2 a t squared. Okay. This, it starts off with an initial velocity of 0, so that's 0. So a is 2x minus x naught divided by t squared. 2 into 10 meters. Okay, so that is the acceleration of this guy, and we'll equate that to that and then calculate I center of mass. All right, so this works out to, the center of mass acceleration works out to 2.96 meters per second squared. All right, so, but the center of mass acceleration is equal to g sine theta divided by 1 plus c. This divided by that is c. C is what we want to find, okay? All right, so by the way, g sine theta, let's calculate that separately. That's 9.8 meters per second square times sine 30. Okay. Okay, so what that is if you had an ice cube, it would slide down with an acceleration of 4.9 meters per second square. So this guy is sliding down at 3 meters per second square. Okay? Okay, so you multiply this by that, and then so this will work out to 1.94 divided by 2.96. 4.96. Okay, again, if you do all the algebra, that's what it should work out. 4.9 minus 3 is 1.94. Okay. Okay, so C works out to 0.66. Okay, again, for a sphere, it's 2/5 mr square, which is 2/5 is 0.4 mr square. For a disk, it is 0.5 mr square. For a ring, it's 1 mr square. So our C is 0.66. It's somewhere between a disk and a ring. Okay? So that's our object. All right. We'll do 2 more problems. So this is sort of the opposite. A solid cylinder rolls up. So this is a cylinder, and even though it's not explicitly stated, a uniform solid cylinder. Okay, so I will be 1/2 mr square. Okay. Rolls up an incline at an angle of 20 degrees. If it starts at the bottom with a speed of 10 meters per second, how far up the incline does it travel? Okay. Okay, how far up the incline does it travel is the question. All right, so its acceleration will be in that direction, and the acceleration will be g sine theta divided by 1 plus I center of mass divided by mr squared. Since it's a disk, the center of mass acceleration is that, and that divided by mr squared is 1/2. 1 plus 1/2 is 3/2. So the center of mass acceleration is g sine theta divided by 3/2. Okay, so if it was an ice cube sliding up, the acceleration would be g sine theta. Since it's rolling up, the acceleration is smaller by that factor. Okay. So we can calculate this. Center of mass acceleration is 9.8 times sine 20 divided by 1.5. So the acceleration of this object rolling up is sine 20 Okay, so this works out to 2.23 meters per second squared. All right, so now this will be our x-axis. There is the initial velocity, and so we'll say this is x naught, x minus x naught. No, what we'll use is this v square equal to v naught square plus 2a x minus x naught. The final velocity will be 0 at the top. Okay, so that'll be 0. Initial velocity is 10 meters per second. All right. So x minus x naught, that's the distance it travels up the incline, is 0 minus 10 square divided by acceleration was 2 times negative 2.23 meters per second square. So it's minus 100 divided by minus 4.46. So it'll go up an incline of 22 meters. Okay, up the incline 22 meters. Okay, so 10 meters per second is 25 miles an hour. Okay, so if you roll up a cylinder, 22 meters would be from that end to the roof there. You roll up a drum at 25 miles an hour, it'll go up that high. Okay. A Formula One race car with a mass of 750 kgs. That's pretty good. 750 kgs. A small car is probably about a little over 1,000 kgs. So these cars are light. Okay. Is speeding through a course in Monaco and enters a circular turn at 220 kilometers per hour. That's roughly about 150 miles an hour. You got to be good. I would be scared driving on a straightaway at 150 miles an hour. Yep. And these guys are making turns and with somebody 6 inches from them, right? In the counterclockwise direction about the origin of the circle. At another part of the course, so at another part of the course, the car enters a second circular turn, also in the counterclockwise direction. 180 kilometers per hour. The first turn is radius is 130 meters, and the second, the radius is 100 meters. Compare the angular momentum of the race car in each turn about the origin. Okay, the angular momentum. So turn one. Turn two. You saw that angular momentum is mass times velocity times r. Okay. So, but let's convert these speeds. 220 kilometers per hour would be, you want to convert this to meters, that's 1,000 meters, that's 3,600 seconds. So it's just dividing this by 3.6. Okay. All right, so L1 is mv1r1 equal to 750 kgs times V1 is 61.1 and radius was 130 meters. Yeah. So units would be kg meter square per second. Kg meters per second times meter square per second. Okay, those are the units, and they don't have any name, so this combination of units doesn't have any name. So you can apply for your name to be named after that. So the angular momentum is 5.96 into 10 to the power 6 in those units. The angular momentum about turn 2 750, the speed is 50 meters per second and the radius is 100 meters. Okay, 2 3, okay. So the angular momentum is 3.75 times 10 to the 6 kg meter square. Okay, so the angular momentum is almost, well, 2/3 of the peak angular momentum. Okay, we'll calculate one more thing the problem doesn't ask, the centripetal acceleration. Anybody Formula One fans here? Do you understand the race? Okay, so 28.7 meters per second square. .93 Gs. That's pretty sick, actually. So you're turning like that, and you're being pushed in this direction towards the center by 3 times your body weight. And I guess those tires are sticky. Wow. So it's like if you inverted the car, the tires are sticky enough that they'll hold the weight of the car. All right? They would actually hold 3 times the weight of the car. All right, AC2 Okay, so the acceleration, the centripetal acceleration around 2 T's is only 2.5 G's. Okay, it's the stickiness of the tire that's providing you the static friction is providing you the centripetal force. Okay, so the tires were sticky enough, you could have gone faster around that turn, and you didn't. So you left something on the table. I guess it's a safety issue. It's a sharper turn, it's more crowded, and that's probably why they didn't turn faster. Because you guys see that they could have turned faster. Okay. Your tires were sticky enough to provide you with that centripetal acceleration. Yeah. All right, guys.